Welcome back. Let's look at another problem. So, a radar tracks Starship throughout its trajectory. When alpha is 55 degrees, the radar tracker reports the following values. R is 25,000 feet. R double dot is 87 feet per second squared. Alpha dot is 0.1 radians per second. From the given information, determine the magnitude of the rocket's velocity and acceleration. And so we will assume that the rocket launches vertically. Okay? So whenever I look at this problem, I think it's just screaming to use polar coordinates. So, we're given our radial vector here, and we're given some theta or alpha angle here. And so if we recognize that, we can use the polar coordinates equations that we know for particle dynamics. And you can see I listed them here in the governing equations tab. So as normally, I like to just write out my givens and everything I know. So we'll do that real quick. So we know alpha is 55 degrees, R is 25,000 feet. We know R double dot, which is 87 feet per second squared. And we also know alpha dot is 0.1 radians per second. Okay? And so what we want is the overall magnitude of the rocket's velocity and acceleration. And so if we assume that it's always going to be pointing upwards or in the vertical direction, we know that the acceleration and velocity point in this direction. Okay? And so really this problem just boils down to another vector decomposition problem. So let's examine our velocity first. I'll pull up my little box here, so try and stay a little bit more organized. Okay, I'm happy with that. There we go. All right, so if we look at our velocity here, I'll start off with drawing the coordinate system that we're working with. So we had x and y. We also had r and theta. We decided that we were going to work with polar coordinates, so let's draw those in. And again, if we're going to use a coordinate system, they have to be orthogonal to each other. And so there we go. I'll draw those in. So we have y and x, and we have positive r, and we'll call positive theta pointing in that direction. So I'll finish drawing these out. Okay. And so we know our velocity is going to be pointing like that, right? We said we were going to assume that it was vertical. And so if we want to break it into its radial and theta directions, all we got to do is drop it down so that we have two orthogonal velocities such that we can use the standard vector addition head to tail idea, and we can achieve that. So there is our velocity triangle. We have v theta and vr. And just to clarify our picture, this angle right here is alpha. And so because x, y are orthogonal to each other, this angle right there is 90. So if we write in this angle between the y direction and the radial direction, we can call that angle gamma. And so from inspection, we see that gamma is going to be equal to 90 minus alpha, which means that gamma is going to be 35 degrees. Okay? Now maybe I'll just redraw our velocity triangle here. It's not perfect, but I think it gets the point across. And we have gamma here. So I'll just draw that in, and just to make it a little bit more clear. And so from our simple trigonometry, we can write that Oh, there we go. Just to make it a little bit more clear, we have that 90-degree angle there. We can write that VR is going to be equal to V cosine gamma, and V theta is going to be equal to V sine gamma. Okay, well, we don't know what V is. The point of the problem was to find V. However, we do know from our governing equations, we know what VR is, and we know what V theta is. And so while we are not explicitly given R dot, we are given R and we are given alpha dot, which to keep consistent with how we wrote our governing equations is going to be theta dot. So if we look at V theta, we know that this is going to be R alpha dot, which is equal to V sine gamma. And so therefore, V is just going to be equal to R alpha dot over sine gamma. And if you plug in our values from the givens above, we can see that our velocity is about 4,358.62 feet per second. Okay, so Starship is cruising along. All right, cool. So I'll get rid of this box, so I'll just break the page up again. Now we're just going to do the exact same thing for the acceleration. So if I draw my acceleration triangle now, we said we were going to assume it points straight upward. We have some component in the radial direction, and we have some component in the theta direction. We'll try and clean this up a little bit. Okay, sorry, those arrows look a little rough, but I think the idea is there. So we have A theta, and AR. And as before, we have this is gamma in between the vertical direction and the radial direction. So again, we can just write AR is going to be equal to A cosine gamma, and A theta is going to be equal to A sine gamma. But if we look at our governing equations here, let's see what we know. If we look at AR, we know R double dot, we know R, and we know theta dot, which is alpha dot. If we looked at A theta, we do not know the angular acceleration, so we wouldn't want to use that expression. So if we go ahead and look at I'll zoom back out, the radial component, right? We got that if AR is equal to A cosine gamma, and then AR is equal to R double dot minus R alpha dot squared, finish that expression up, then we know that just dividing through by cosine gamma, we get an expression for the acceleration. And if you go ahead and plug everything in, you'll see that the acceleration is negative 198.98 feet per second squared. Okay. And so that's it for this problem, but I'd like to just point out something real quick. So I realize that I just kind of chose numbers and randomly threw them into this problem whenever I created it. But if anytime you solve one of these problems, you should always ask yourself, does my answer physically make sense? So if I have this rocket going up, and we would imagine it's accelerating, perhaps this negative acceleration here, perhaps that's not correct. Does that make sense? If we convert this to G's, we see it's about 6.17 G's. So that's a lot of deceleration for a rocket that's supposed to be breaking through the atmosphere. So is that correct? Is that value correct? I don't entirely know. Like I said, I just threw in values. But if you're the engineer behind this project and you calculate that that's your acceleration, maybe you might question, okay, well, is our angular velocity of our radar, is that correct? Or you might question, how good is our tracking, and is our radial distance correct? These are some questions you might want to be asking yourselves. And it's just something to keep in mind as you proceed through similar problems like this. You always want to make sure that your answer is making physical sense, and if it isn't, perhaps you can try and find an error in your logic or in your measurements. But yeah, so to conclude, this problem was just basically another vector decomposition problem, and we made use of polar coordinates to solve. So I hope this was helpful, and I hope you stick around for the next video. Thank you.